Unit 1T, Block 11. And so I call this 1T because it's a transition topic between Unit 1 and Unit 2. So we're talking about the idea of slope, just as you know it, and how that relates to the topics in Unit 2. So the information in this unit, it's not part of the scope and sequence for College Board and for the AP exam, but the idea behind what's happening is definitely a part of the scope and sequence. So it's kind of like it's a really good lead into Unit 2 and why Unit 2 is the way it is. So I want to spend a couple of days just going through the reasons why Unit 2 is the way it is. So these notes start on page 35 of your packet, and the title of this is Rates of Change and Tangent Lines. And the essential question is, how can we calculate slope with only one point? So if you think about that and what you know about slope, take a moment to think, and you might realize that if I only had 1 point, that might be a problem, right? So, but we need to be able to do this. So we need to be able to realize that that this is a possibility. So looking at slope, and we're gonna approach slope as instead of calling it slope, we're gonna call it a rate of change, right? And so we're familiar with We're familiar with rate of change as being rise over run, or y2 minus y1 over x2 minus x1, right? Those are all the ideas around slope, or f of b minus f of a over b minus a. Okay, those are all ways we can calculate slope. So, but we're going to refer to the slope as rate of change. And so what we're doing when we use that rise over run is we're calculating the average rate of change. So if we look at the definition here, it's the average rate of change of a function over an interval is the amount of change, right? Those are the y values, divided by the length of the interval. Okay, so if we look at that, it's the amount of change of the function, those are the y values, divided by the length of the interval. And so, as you can see, this requires 2 points. But we want to be able to calculate slope with only 1 point. So, so right now I guess you could say we're short a point. And so we could also call this rise over run, right? We could also use function notation and say f of b minus f of a over b minus a. Okay, and so I refer to this as the algebra slope, or just slope. This is also referred to a little more mathy as the slope of the secant line. So a secant line is a line that we draw between 2 points. And since those 2 points would be on the function, then what we're drawing is a line that touches the function in 2 points, and that's called a secant line. It's also an average rate of change. So anytime you incorporate 2 points, you're calculating an average. You're taking the slope of that straight line between the 2 points. In other words, relative to the function, if we calculate the algebra slope, we're saying we're not going to pay attention to the function. All we're going to pay attention to is the slope of that straight line. So that's why we call it an average rate of change, because it doesn't really represent the function specifically. And you could also refer to it as an average velocity, because velocity is a rate. So if we had position and time information, then calculating the slope would be the average velocity. And then here's the big star. College Board refers to this a lot of times as a difference quotient, because if you take a look at this expression right here, right, difference means subtraction and quotient means fraction. So that's an accurate description of what this expression represents. It represents a difference quotient. And in fact, working on the review problems for the Unit 1 exam, you might have seen my note about when you were asked to write a difference quotient on one of the free response questions. And the note was something like, we're going to have to learn how to do this, and we'll do that during the transition unit. Okay, so let's talk about applying the average velocity or the average rate of change in this context. So we have some function data here that's a parabola, and it says calculate the average velocity of the insect over the domain from 1 to 4. Draw the secant line representing this value. So the context of this problem is that this function represents the position of an insect as it crawls on a picnic table. So being the context being like a physical representation of an insect crawling, of course this part of the parabola wouldn't make much sense because it's negative time. So here's the insect at time t equals 0 at the origin, and then it looks like it crawls away from you to a position of negative maybe 2 point something. So maybe it is about 2 and a little more meters to your left, and then it turns around and comes back to you, and then it crawls past you to the right. So that might represent the motion of the insect. And so we're going to calculate the average velocity, which means we're going to calculate the slope of the secant line. So we're going to go ahead and look at, identify that the domain is from 1 to 4. So we need those 2 points. And I'm going to draw it right now. There's the point at 1. There's the point at 4. And the slope of that straight line represents the average velocity, right? That's the slope of the secant line, or what I would call the algebra slope. So I'm going to call it average rate of change. I'm using more of the calculus vocabulary now instead of algebra slope. I'm going to call it the average rate of change. And so I'm going to use the function notation of the algebra slope, right? This is y2 minus y1 over x2 minus x1, but this is the function notation. And I'm going to plug in those values. F of 4, looks like f of 4 is at 4 itself. F of 1 is negative 2. So we're going to put those values in, 4 and negative 2. And then we're going to simplify this. So let's just pause right here and let's talk about a difference quotient, because that's the other vocabulary that the College Board uses. So average rate of change in this context, difference quotient would be the two vocabulary phrases that College Board would rely on. They wouldn't use algebra slope. And so this represents a number, and I mentioned this in the review presentation also in class. And you can leave the value like that. When College Board asks you to write a difference quotient or find the difference quotient, if you leave your answer like this, that's perfectly okay. You don't have to simplify it. That's for the grader to do. So that's a mathematically correct expression, and it's all numeric, so you can leave it like that. For the context of the notes, I'm going to simplify it. So the top ends up being 6, and the bottom ends up being 3, and 6 divided by 3 is 2. And we can see that on this line, right? We go up 1 over 2, up 1 over 2, up 1 over 2. We know it has a slope of 2. So the average rate of change is that this bug, on average, is traveling 2 meters per second through these 3 seconds. Now, the bug doesn't actually do that, right? The bug actually travels away from us and then stops and turns around and travels back towards us, really, in that time. So this average rate of change is not an accurate representation of what the bug is doing. And if we want an accurate representation of what the bug is doing, then we need to follow this bug point by point, which means we need to follow the bug with this one point as it traverses through this function. And so that's the idea of calculating slope of a line that just goes through one point. And that involves limits. So to answer the question now, that's the bug's average velocity, because we know velocity is a rate. Okay, so that becomes, here's our kind of our essential question as it pertains to this example. Can we calculate the slope at location x equals 1? So if we're going to use just one point, that means we no longer are talking about a secant line, but we're talking about a tangent line. And if you can estimate a tangent line, right, tangent touches the curve in one point. If we try to draw a tangent line here, then that definitely doesn't have a slope of positive 2. In fact, the tangent line's slope is negative. So it's a very different answer. So the question is, how do we get that answer? So let's take a look at what's happening. And you can pause on your notes here, just be kind of an active listener. So I've set up the function from that last example. I set up the secant line, right? Here's t equals 1, here's t equals 4, here's my slope calculation. But what I really want is this tangent line. And like I said, that involves a limit process. So I'm going to go ahead and start the video, and what's going to happen is we're going to move this point. Now notice I have this point that it says a plus h, right? That's really at 4, right? The a is over here, that's this location. So this is really 1 plus 3. And the h represents the distance between the 2 points horizontally, right? The original point's at 1, this final red point's at 4. So this is 1 plus 3, which makes 4. Okay, so we're gonna, if we want the tangent line right here, we're gonna take this point and we are going to slowly move that point over here back along the function so that it meets up with this point here. Okay. And so as we move that point back, watch the slope change, right? Watch the slope between the points change. It's getting flatter and flatter and flatter. And I can actually find a point here where the slope is 0, right? At the between 1 and 2 seconds, the bug was in the same location. And now as I bring it back, look at this slope value. And as I bring it back to that point of tangency, we saw that slope value get really close to -1. It's approaching -1 if I would use my my limit vocabulary. So let me just kind of back up the video here to get some numeric values. There we go. Right, this is getting really close. When these 2 points are really close together, let me just spread them apart enough for you to see. That's pretty close to tangent. So that's pretty close to the slope of the tangent line. But what happens is as we get closer and closer, these two values are getting to be the same, right? We're going to get 0 over 0, which we know is indeterminate. So we no longer can calculate the algebra slope. And so as we bring them together to that point of tangency, that's 0. That's going to be, you know, -2 minus -2 over 1 minus 1. That's going to be 0 over 0. There's our indeterminate form. And so we'll get to process that indeterminate form, we're going to have to do a limit method on this difference quotient. And so that's what we're really going after, is how do we take this difference quotient and apply the limit. Oops, let me get back to here to pause that. There we go, now it's paused. How do we apply this difference quotient and take the limit of it so that we can find the slope of that tangent line? And so that's the process that we're going to go through these 2 days. So the average rate of change, written in function notation, looks like that, right? It's y2 minus y1 over x2 minus x1, right? Here's y2, it's up here, that I've moved the point, but the y2 minus y1 is where that point started. Let me back up the video, right? There's x2 comma y2, right? And here's x1 comma y1. So there's the average rate of change. And the slope at a point then is taking that average rate of change and taking its limit as this gap h shuts down and goes to 0, right? That's what's happening here. H is getting, now H is right here, right? That's the width between the points. So that width between the points is shutting down and going to 0. But we know we have a fundamental problem when it goes to 0 because it becomes indeterminate. So we have to use our limit strategies then to evaluate this. And when we evaluate that, then we have found the slope of that tangent line. So that's the process we're going to go through. So that gives us to our first definition here, the slope of a curve at a point. The slope of the curve of that point, at that point, which would be the tangent line, okay, is that expression. Now we're starting back with the notes again, is that expression where we take the difference quotient and take its limit as that gap closes, as h goes to 0. I think I overlooked something. Let me go back to here. Sorry, I just need to mention this. So notice that it's just an h. We don't have a difference in the denominator anymore. We did start out with a difference, but I simplified it. So a plus h minus a is just h. So that's why we don't have a difference represented in the denominator anymore. But it's still a difference quotient because we can see it right here. Sorry about that. So this is our difference quotient. This is our algebra slope, but we're going to take the limit of that. And that's going to give us our tangent line, because when h goes to 0, that means those 2 points have been brought back together. So there are some synonyms here for slope of a curve at a point. It's the slope of the tangent line, right? It's that line that's only touching, like if we go back to the bug example, it's only touching at x equals 1. So it's a tangent line. It's the instantaneous rate of change because it's still slope. So it's still a rate of change, but it's a change at one point, just x equals 1. So we call that an instantaneous rate of change. And so what we do is we still use the ROC acronym, but we don't have the average anymore, right? The instantaneous is just the ROC. We call it the instantaneous velocity, or just velocity. We tend to drop these instantaneous descriptors when we're implying it's instantaneous if they're not there, if average isn't there. So we're going to use our limit strategies to calculate these values, because we now have a limit process. And so I call this the limit method. That's my own vocabulary. There's really not a official vocabulary for it, but I call it the limit method. I guess the official vocabulary would be the slope of the curve at a point. So let's do this. Let's take, so we're on the next page of notes now. Let's take that bug example and see if we can calculate the slope of the tangent line algebraically. We know it should be -1, right? We saw that in the video. So we have this function, t2 minus 3t, and that's the position function here. That's the parabola. And we want to find the instantaneous velocity of the bug at time t equals 1. So we want that slope of that tangent line. So like I said, I call this the limit method. So in the notation, we need to identify what a is. Because of the notation, let me go back to that previous page, right? We need an a. We need to identify our starting point. So the a is where we started, and we started at t equals 1. So a is 1. And so now I need these two possessions. So the idea is that this point is coming in, and look at this, the points here are just slightly moved, right? We're no longer at 4 anymore, because if we were at 4, we would know what our position is. So we've got this random point here that is transitioning back to x equals 1. So this distance between the 2 points then isn't really a numeric value anymore. It's just h. It's whatever that horizontal distance is, whatever the difference between the x coordinates is, and that's changing. And so we come up with expressions. We know a is 1, so we can find f of 1. And we can find f of 1 plus h. So if a is 1, we're going to put 1 here. F of 1 plus h is going to be 1 plus h squared minus 3 times 1 plus h. So that's f of 1 plus h. Okay, so take a moment to simplify that. That's the first part of putting together the limit expression. So go ahead and pause the video and simplify that. Expand this out, right? FOIL and distribute and combine. Okay, if you're coming back, I'm assuming you've tried that. Now you can check your work. So this is x, excuse me, not x. 1 plus h squared is 1 plus 2h plus h squared. And then this is minus 3 minus 3h. So 1 minus 3 is minus 2. 2h minus 3h is minus h, and then we have the h squared. So that's the simplified f of 1 plus h value. And then we need f of 1. So plug in 1 here, and we get 1 squared minus 3 times 1, and you can calculate that on your own, but that's negative 2. So these two represent the two values that go in the numerator of that expression. So we're going to use that definition. I am not sure what's going on right here, but this is how we set this up. We set up the limit expression, and then we plop in that f of 1 plus h. So there it is, and then we put our, this is really important, we put our minus sign here, and then we have to put in the f of a value, okay? And the f of a value is negative, so I'm going to use brackets so that I make sure I distribute that negative sign, and then it's all over h. So now we simplify the top, right? And this will always happen. This is the cool thing, is once you do this substitution, this number and this number should go away. Let me back that up, right? We have a negative 2 plus a negative 2. This is plus 2. So we have negative 2 plus 2. These will always disappear. That's how you know you've done the simplification of f of a plus h correctly, okay? So we're going to cross those out, and we're going to be left with this expression. So we have minus h plus h squared all over h. So that's, now we have to rely on our limit methods, right? What would we do? We know if we plug in 0, we get 0 over 0. So it's indeterminate. So we need to either factor or use our conjugates or use some trig. And this is a factor problem. So we're going to factor out an h on the top. So I factor out an h and have minus 1 plus h over h, and I can cancel then common factors, right? I'm canceling the whole, just like we were doing in Unit 1. And so now I'm left with a simplified expression of minus 1 plus h. And now I can use my direct substitution. I can put in 0, and excuse me, and I get negative 1. Okay, so there's my instantaneous rate of change. Notice what I did here. I started calling it slope, right? The m. So my slope is negative 1. I'm not quite sure what's going on over here. So I think, and so that's the instantaneous velocity. I think this was, yep, okay, so I've got some problems here with the video, but if you could just kind of visualize the parabola right here, and that blue spot is x equals 1. So we're down there at 1, negative 2. And then I'm going to do this. I'm going to go down 1 and right 1 off the, on the grid. And I'm going to, after going down 1 and right 1, I'm just going to draw a line through that. And then this line is going to end up being tangent to the function at the blue point. Must have a little glitch there in the presentation. Okay, so now here's the other really critical skill that College Board really expects you to know how to do really well. And this question, writing the equation of the tangent line, is a question I will ask on every exam going forward. You'll have to write the equation of a tangent line. And I have some scaffolding, some supports for you in the classroom. And writing the equation for the tangent line is an anchor chart at the front of the room, right in the middle of the room, so that you always have that, you're always looking at that. So writing the equation of a tangent line involves knowing the slope and a point. So we know that we are at 1, negative 2 at the beginning, right? That's our a and f of a. and we just calculated the slope of the tangent line. And so we're going to use the slope point form. Oh, hey, this actually helps. So that thing that was messed up on the previous screen, I'm doing right here. So if you didn't draw the tangent line at the beginning of example 2, then you can draw it now, right? Here's point A, and the slope is -1, so I'm going to go down 1, and right 1, and I'm going to draw that tangent line. So now we can see it's that this has a slope of -1, and it's tangent to the function, right? Here's the function in black. It's touching the function at one point. It's tangent to the function when x is equal to 1, or when t is equal to 1, if you want to use the context of the problem, right? T is equal to 1. Okay, so this is by far the easiest way to write the slope of a tangent line. That's the slope point form. The slope-intercept form is super clunky and super inefficient. We don't use it at all in calculus. The reason why we use the slope point form is because once we write this down, we just plop in m and plop in x1, y1, and we're done. So there it is, -1, x is 1, y is -2. There it is, we're done. We don't have to do anything with that. And the reason why this is so convenient is because we have the slope and we don't have an intercept, right? The intercept is right here. And so to find that would require extra math. Why do the extra math? You don't have to. We'll just use this form, and we'll use this a point that is on the line. And it just doesn't happen to be the y-intercept. So that's done. That's how easy it is when we use the slope point form. The next question says, write the equation of the normal line. Sometimes they ask this. Normal means perpendicular, so a line that's perpendicular would look like this, which means its slope is the opposite reciprocal, right? The opposite meaning positive, reciprocal meaning take 1 over 1 and flip it, which means we still get 1. And so the cool thing is writing the equation of the normal line just means changing the slope value. Everything else stays the same, right? Because all we're going to do is we're going to draw a perpendicular line through that blue point. And there's the normal line. So using that point slope form is a very efficient form. And so those are the skills that we need to work on for the next 2 days. Is the limit method, and then writing these equations for the lines once we get our slope. Okay, so let's try this again. So this is just another example with a slightly different type of parabola. Quite honestly, to do this with anything other than a parabolic curve is really mathy and really complicated, so I don't ask you to do it to anything that's more complicated than a quadratic. Okay, so let's kind of get a little bit of fluency here. We're setting up the limit method, right? Which means I need f of a plus h and f of a. In other words, I'm filling out that slope expression in the definition, right? Well, how much is a? A is where we're starting. Okay, well, a is at 4. So a is 4. Right, it's where our point is, where we're starting. So I want to find the slope of that tangent line. So that tangent line's pretty vertical. I would expect to get definitely a number bigger than 1. Okay, it kind of helps to get a little physical, a visual representation, and just to know that, you know, whether or not your answer's in the ballpark. All right, so we're going to plug 4 in for a. So f of 4 plus h. So I'm going to put 4 plus h here and square it, and 4 plus h here, and I'm going to be really cognizant of using my parentheses, my brackets, okay, so that I'm distributing numbers appropriately. So I have 1/2, right, 1/2 x of 4 plus h quantity squared minus 2 times the quantity 4 plus h. So there's my f of 4 plus h, and then I'm going to simplify that, okay? So pause the video and try to simplify that on your own, and then start the video and we'll go through the simplification. Oh, I guess I didn't go through the simplification. Wow, I didn't go through the steps here. But, you know, expanding 4 plus h out is going to be 16 plus 8h plus h squared. So we're going to have 16 plus 8h plus h squared, and then we're going to have minus 8 minus 2h. So 16 minus 8, and then we're going to take half of this. So it's going to be 8 minus 4h, or 8 plus 4h plus half h squared minus 8 minus 2h, so that's how we get the positive 2h. And then the half h squared doesn't combine with anything. So there's the answer of f of 4 plus h. I should have had more steps there. You'll get an opportunity to practice those steps in class. Okay, and then f of 4, put 4 in here. Whoops. F of 4, should have put more steps there too. So if we put 4 in, I'm up at the top of the screen now. If we put 4 in for x and square it, we get 16. Half of 16 is 8. So this first part is 8. And then if we put 4 here, we get minus 2 times 4, which is 8. So we get 8 minus 8, which is 0. So notice, this is interesting, but we have a 0 here and a 0 here. And I'm keeping the zeros for just a moment here. So I'm going to put the 4 plus h here, minus the 4. I know it looks a little hokey, but I want to stress that these two numeric values should be the same, and they are. They just happen to be 0. That happens sometimes. And so they're going to cancel. These will, if you did all of this simplification correctly, these two numbers will always be the same and they'll always cancel. And the reason why is because if they didn't cancel, then we couldn't factor this and cancel the h on the bottom. So these have to go away in order for that factor and cancel step to work. So we're going to re-express this. We're going to simplify this by factoring out an h, right? So we have 2 times the quantity, or excuse me, h times the quantity, 2 plus half h over h. We're going to cancel our h's. So now we have the limit of 2 plus half h. We're going to put 0 in for h. And so we have a limit of 2. So this is approaching a slope of 2. So that means I can draw this tangent line, and I can go over 1 up 2 and draw that line in there. We're going to have a point right at that intersection right there. Okay, so we have our x1, y1. If we plug in 4, we get 0, right? We can read that right off the graph too, right? 4 comma 0. We have our slope. And so we can write the equation of our tangent line. So we're going to plug in the slope of 2. We're going to plug in my x-coordinate of 4 and our y-coordinate of 0. And then if we want to write the equation of the normal line, oh, and I just put in the picture here. Here's the point of tangency, and then I'm going to put in that line and see how we over 1 up 2. There, it goes through that point right there. So that's the slope of the tangent line. And then we can write the normal line by just taking the opposite reciprocal of 2, which is negative 1/2. And then it goes through the same point, so nothing changes here. And then we can come back to the picture and draw a line with negative 1, right down 1, right 2. So a slope of negative 1/2 there. Okay, so two big skills: finding the slope of the tangent line and then writing the equations. Slope is a number. The equations are equations. They have x's and y's in them. Okay, so this last example is kind of funny, kind of cool, but it says we're going to do this process again. Find the slope of the tangent line to the graph, and here's the function. So this is not a quadratic anymore. And we're talking about at x equals 2. So pause for a second, look at this function. What is this function of? Okay, so I'm intentionally not drawing a picture for a reason. And that is, you know, a couple of reasons actually, but a big reason is that we don't always give you the opportunity to see a graph, right? So you might know what this looks like, you might not know what this looks like, and at the end you'll have a big aha moment. Okay, so let's go through the process here. I need f of a plus h. So looking at this question, what is a? Think about that for a second. Okay, if you said A is 2, you are correct, right? That's the point that we are concerned about. And so f of 2 plus h then is plugging 2 in right here. So 3/2 times 2 is 3, right? Plus h, 3/2 times the quantity 2 plus h minus 4. And go ahead and simplify that. And when you simplify that, you get 3/2 times 2 is 3, right? 3/2 times h is 3/2 h. So I've got 3 minus 4, which is 1. So there's the expression simplified. Now we're going to plug in 2. And when we plug in 2, we get 3/2 times 2 is 3. 3 minus 4 is negative 1. So our expression looks like 3/2 h minus 1 minus a negative 1. Okay. So because of the way this is written, the constant ends up here instead of being first. But it still cancels, right? Minus 1 minus negative 1, this is plus 1, right? Minus 1 plus 1, those still cancel. So here's our expression for our slope of our tangent line, or instantaneous rate of change, however we want to call that. And we end up having 3/2 h over h. And so we don't even have to factor because we only have a single term above. We can cancel the h's, and we have a slope of 3/2. So now pause and look at the slope and look at the function. So if you realize that this function is a line, and the slope of the line is 3/2 and the y-intercept is negative 4, which doesn't matter. But if you notice that, if you know that, the slope of a line is constant, then any quote-unquote point of tangency will have the same slope. If I pick a point and that point is on the line and I try to draw a line of tangency, it's just going to be the line itself. So in this situation, if you realize this was linear, we didn't even have to go through the whole limit method. We could have just picked this number out and know that that's the slope. So notice I didn't ask you to write the equation of the tangent line because you'd just be writing this equation over. You would just in slope point form. You would have just done 3/2 times quantity x minus 2 plus a negative 1. And so I didn't ask you to write the slope, the equation for the tangent line for that reason. Okay, so those are the skills we're going to practice for the next couple of days. And when we get back into class, we'll go over the takeaways. And so we're looking at that limit method, and we're looking at writing the equation of the tangent line. I'll see you in class.